Cool. How's everyone doing? And you're not doing a traffic light lab, so you're doing even better than you might. But amazingly is great. All right, let's talk about PA4. And office hours are getting pretty crazy right now. My 250 class is working on their hardest lab and homework of the course. I haven't told them that, so don't tell them. But yeah, they're working on some really major stuff. And you know, lots of advising going on with registration open and people trying to figure out fall and so on. So office hours are getting pretty busy. So yeah, we can definitely do a lab day on Thursday, although hopefully people are in really good shape before then. But if you need help finishing things up, Thursday we'll do a lab day. 250 are working on the full traffic light, which is the three-way intersection, including the delayed yellow light. And we're doing state machine synthesis and analysis homeworks. And so those are typically, you know, long multi-page, multi-hour assignments. So lots of good questions coming up in there. So PA4 questions. Having an issue where Eclipse is not displaying anything on my design tab, so I can't utilize drag and drop. Yeah, I've had that happen. And sometimes it's non-understandable flakiness, but most of the time when that's happening, there's something going on in your code that might work fine when it's running, but that's doing something that might not be initialized. For example, let's suppose that your code is reading your box array and displaying lines based on that. When you switch to the design tab, Window Builder will look at your code and try to draw the display, but if the box array, you know, is something that's constructed at runtime, it may get stuck on that. Whereas in your code, if you put in a simple if statement that says, you know, if box array is not null, then let's iterate over the boxes in there and do the painting, sometimes that'll get you out of it. And so you can try, you know, removing sections of your code, commenting them out. Anything that could be causing a null pointer exception is a good thing to try commenting out and see if that brings it back. And then if it does, throw some conditionals in there so that Window Builder can get past it. My dots are still appearing in the design but acting weird or gone in the executable. That's interesting. So if it's showing up in Window Builder but not in the executable. So I would say make sure you're calling repaint. Make sure you're calling super.paint in the beginning of your paint method, because it may be that you're not refreshing the panel completely, and that can be tripping it up. That would be my first guess. The issue only comes up when one or two extra conditionals, but they seem to be working as they should. I don't have a quick theory for that. That's definitely good office hours. All right, what else? Hey, it's raining. Big surprise. Still sunny here. Okay. Yeah, it's been colder and it's been getting darker. And just before class started, it was downright like if I was East Coast, I'd be worried about severe weather. Um, don't know the reference. Oh, excellent. How about mapping, as in like mapping clicks to coordinates and boxes and lines? Yeah, yeah. So let's picture a grid. Yeah, so someone else was saying they made all of their lines objects to give them mouse events, but that's a lot of mouse events and that's hard to scale. Um, and this mapping from coordinates to locations inside a grid, for example, is something we'll encounter a lot with GUIs, with game development, things like that. And it's the inverse of a graphics problem, which is how do you draw things corresponding to certain, underlying grids and such. So let's imagine, 50 by 50 boxes, and let's think about coordinates. So, 0, 0, 50, 0, 100. Right, and so on. Want to do it with a hash map, but keys don't work with ranges. You could do that. You could make a class for storing a range, and make those the keys or values of your hash map. But yeah, looking them up directly wouldn't work. But you might be able to make a hash of keys. There's a lot of ways you could do this. You could, yeah. And again, right, so in your case in particular, I ask if you're doing this for fun or because you don't know a different way to do it. And that the answer to that sort of affects my answer. Yeah, you can scale. You can automatically create objects. I mean, wouldn't scale if, for example, you wanted a 5,000 by 5,000 game of dots. That would be 25 million objects. I don't know if that's going to give you a performance hit in Swing. Whereas if you had a single panel, you can scale it up more or less indefinitely and just do the math. Oh, multiple players, cool. Okay, doing it for fun, that's cool. Let's see. Yeah, so I mean, I could envision a hash map where, yeah, so you still need some kind of bucketizing. But you could just take your XY coordinates, divide them each by 50, and then put those together with a comma in between. You use that as a key to a hash map, and get back the coordinates of the box, or things like that. I recommend, yeah, that would be a fun one. Hash maps are so cool. I mean, I've probably told you this in 224 when I first discovered one. It became my hammer, right? And everything I wanted to do, it didn't matter if I was doing arithmetic computations, scientific calculations, writing compilers, anything I wanted to do, I just threw a hash at it, right? And you can do so many things with it, and it's just a fun thing to wield. Um, Oh, cool. I'll have to look at that. Would it be a good idea to handle the mouse click within the J frame or make a separate panel? Strongly recommend doing the mouse clicks inside a panel and actually putting a sub panel inside your main panel so that you have your J frame with the boxes. And this has, a panel sitting inside, which is a content pane. I recommend putting a panel inside here, which is like a My panel or a Game panel or something like that. And the advantage of putting the mouse listener inside this thing is that the upper left corner of that region will be 0, 0. And the lower right corner of that region would be 400, 400, or 399, or whatever, right? So it's relative to this. And then I can position this wherever I want and not have to worry about adjusting coordinates from my mouse clicks. And then, I can put buttons out here, and I can put text fields and radio buttons and so on. And not affect my coordinate system inside this game panel. I think we're going to get hail next. Yeah, no, I'll have to check out his one, see what the lines look like. All right, so here's a a 3x4 array of grids, and here's what the coordinates look like. And if each box is 50 by 50, then remember our rows go down, our columns go across. So our x-coordinate is just the column number times 50. Our y-coordinate is just the row number times 50. So x is column times cell width, y is row times cell height. So we can find these numbers easily enough. And now suppose the person clicks their mouse right here at some point xy. So to map that into a particular edge on a particular box, you got to do two things. First thing, find out what box you're in. So one, find row, comma, column. And so the row is just x divided, the row is just y divided by the cell height, and the column is just x divided by the cell width. So let's say that this point here is, 80, comma, 55. All right, so x is 80, y is 55. 80 divided by 50 is 1. 55 divided by 50 is 1. Well, that's pretty unexciting. That tells me I'm in row 0, 1, and I'm in column 0, 1. So I know I'm in this box here. All right, if I know the row and the column of the box I'm in, I can reproduce these numbers. Right, so this is column times 50, row times 50. This is column times 50 plus an extra 50, or column plus 1 times 50, and then row times 50. This is 50 column, 50 times row plus 1, and this is 50 times column plus 1, 50 times row plus 1. Right, so that's just these maps here. And then once you know what the coordinates are for each corner of this, now we can find those four distances. So now we go to a blown up map. I should have used a different row and column. Alright, and the person clicked right here, which was 80 and 55. Guess that would be more like right here. Alright, so now calculate your distance to each edge. So this distance is your x-coordinate of the point minus the x-coordinate of that left wall. So that's 30. This distance is the x-coordinate of the right wall minus the x-coordinate of the point, which is 20. This distance is the y-coordinate of the bottom line minus the y-coordinate of the point, which is 45. And this distance is the y-coordinate of the point minus the y-coordinate of the top line, which is 5. So you've got 4 distances, 30, 20, 45, and 5. This is your smallest one, so this is the line that they click next to. So that's a pretty mechanical way to figure out what box they clicked in and which edge they clicked closest to. And it's up to you what you do if they click, you know, the same distance from 2 edges, which one you pick, or do you refuse to acknowledge that click, or what? And after you've coded something like this a few times, it becomes pretty second nature, and these kinds of arithmetic manipulations start to kind of make innate sense. But the first few times you do this, right, it takes a lot of head scratching, and the first time I tried to do this, right, I was kind of figuring out from scratch, and it took me hours to do, you know, any one of these things, to figure out the row or the column or the line or something like that. It's a different way of thinking about things, but the more you do it, the more it starts to make sense, and it's definitely something that will come up again and again anytime that you're trying to partition an area and figure out where things sit within that. You end up doing these kinds of calculations. All right, so on to networking. Let me get my counter going here. All right, so networking. So everything we do is like networked together, right? We have lots of things that we share, things that we get to remotely, and so on and so forth. We don't even think about it anymore. But you know, so much of what we do is going from one machine to another, and there's different ways to do this, but a surprisingly large amount of these different ways all use the same underlying principle, and most of this is based on what's called a client-server model. And everything we do with networking is going to be basically client-server based. And so the basic picture looks something like this. We have some sort of server. And this is typically a process sitting somewhere, some piece of code running. And then we have usually multiple, but it could just be one. But it could be multiple clients. And the server will do something for these clients. And the action is usually initiated by a client. So the client 1 comes to the server and says, hey, do something for me. And client 2 might say, hey, do something for me. And client 3 could say, you know, provider 3 wants something done also. And so where does this pop up? Well, lots of places. So for example, we have a print server, right? Why do we have a print server? Because, you know, in the old days you had a printer and it had a cable coming out of the back, and the cable went in the back of your computer through a big parallel port. Anybody remember these 25-pin connectors for printer cables? And you'd plug it into a port on your PC, and it would, you know, shove information out to the printer. Well, if you had 2 computers, excellent, and not surprising. So if you had 2 computers, right, what could you do? Well, you know, maybe you could try to get a splitter and have that cable, have the wires from that go off to 2 different cables and plug those into 2 computers. And, you know, you might be able to make that work as long as both computers didn't try printing at once. But if computer 1 started sending information to the printer, and while it was sending it, computer 2 started sending, those signals would interfere with each other, right? And worst case, you know, you might actually burn something out if this is sending a 1 and this is sending a 0. But certainly you're going to get confusion at the printer. And so what you typically have is you have one printer and you have one thing controlling it, a print server. And it could be a program, it could be a computer, but anybody who wants to print doesn't talk directly to the printer, they talk to the server. And the server can go to the printer. Now you only have one thing sending information here, you only have one thing picking up information from the printer, and anybody else who wants to print does it through this server. So client 1 says, hey, I got a job, I want you to print. Okay, it picks up the bytes, it starts sending them to the printer. While that's happening, client 2 says, hey, I got something I want you to print. It says, okay, tell me what you want printed, and I'll take care of that when I can. So it sends its information over, and this thing saves it, right? And client 3 comes along and says, I got something that I want you to print. Well, maybe this thing is filled up. Remembering client 2's job, it's going to say, hold on a second, right? And then when client 1 finishes and it starts printing client 2, now it might say, okay, client 3, tell me what you want printed. I'll get to it. Or maybe you could have 10 clients that could all shove jobs into here before this thing got overloaded, right? So that's one example. And the action is initiated by the clients, and the server is just kind of hanging out waiting for something to do. Okay? So that's a print server. You can have a time server. So when your machine boots up or your phone comes online, it wants to know what time it is. It talks to a time server, maybe out at NIST, maybe at Microsoft, as basically something hanging out somewhere waiting for requests. And the client comes in and says, tell me what time it is, and it sends back a message telling you what time it is. Alright, that's a time server. You can have a web server. And what does a web server do? It waits for clients to say, show me this web page. So I want to see a page called index.html. And the server will look through its file system for a file with that name and open it up, read the contents, send it back to the client. So this is pretty ubiquitous. And this is what happens when we log into a remote machine like the Linux server. Hint, hint, it's called the Linux server. Why? Because it's a server, right? And what's the client in that case? Well, it could be PuTTY, it could be SSH, it could be Terminmux, it could be, you know, whatever you're using to connect to a remote machine. But if you're using PuTTY, PuTTY is not the remote machine. PuTTY is a client program. And it doesn't connect really directly to the Linux machine. It connects to a program running on the Linux machine to affect an interactive session. Who got the surprise Pikachu face? So So how does a login server work? So there's a protocol called SSH. It's a secure shell. So we use Bash, right? In 224. That's the born again shell, which is a play on words for the old shell, which was called SH, which was the born shell, B-O-U-R-N-E, like the born identity. And SSH is a secure shell. So it's a shell that incorporates encryption in the input and output to make it more secure. And so SSH is really a protocol for doing secure shell-like things. And in particular, it's usually used for doing secure shell-like things across a network. And so there's an SSH server. And it's actually sitting in a program called SSHD. And D is for a daemon, which is kind of like a demon, but spelled differently. So there's an SSH daemon. And that's a server. And it's a server that hangs out and waits for clients. And in this case, the clients are a program called SSH or PuTTY or something else to poke the server and say, hey, can you do something for me? Yeah, what do you want? I'd like to log in and run a shell on your machine. Okay, who are you? Oh, I'm Nick. Okay, prove to me that you have access. Send me something so that I know that you're authorized. So you send off your public key, and it does something with that. Send off your private key, and it does something with that, and it says, okay, you're authorized, and it logs you in. Excellent. Yeah. Man, don't you love FFmpeg? It's like super Swiss Army knife. So let's take a quick look on the Linux server. So SSHD, right, is a program under user sbin, and it's process 796. And its parent process is process ID 1. What's process 1? It's a NIT. It's the creator of most all processes on our Unix system. This program started running on March 5th. That's when I last rebooted the machine. So our machine's been up for about 2.5 months, which takes us back to early March. Oh yeah, totally. And of course, you know, SL instead of LS, everyone's favorite. All right, so this is a server program that's hanging out waiting for SSH requests. And it's created a process, in this case, process 41520, which is an SSHD test, that's my user ID, which created another process, which ultimately created this process bash, which is what I'm running right here, this interactive shell. That's a process created by 41530, which was created by 41520, which was created by 796, which is the SSH daemon. So the whole way that we managed to log in and have an interactive session is because we run a client that talks to the server on this particular machine, linuxengrcs.com, and that server does some authentication and then creates a new process to run, in my case, bash, and connect whatever comes in from the client to the standard in of bash and takes standard out from bash and sends that back to the client, and SSH displays it. So we use this client server setup all the time. And the whole thing is built upon this idea that we can have a program running out here, but we can have something that a client can send information to. There's got to be some kind of portal over here through which information can be sent and information can be received. So we really need two things to make this happen. One, we need to identify a machine on the net. And two, we need to identify a portal, or it's actually just called a port, on that machine that we want to send information to, get information from. Alright, so how do we identify a machine on a network? We need some kind of address. And we usually talk about IP addresses. So an IP address is something like, 192.168.0.101 or 10.0.0.4 or 26.0.1.2. So it's IPv4 version 4 is this 4 number address. And every machine that's connected to the internet has a unique 4-part address. But, most of us live on a local network, so if you have a router, you have a bunch of machines connected to that router. Each machine has its own address, but it usually looks like something like 192.168.0 something, or 1 something. And I don't know if port is short for portal. I never said that out loud until 2 minutes ago, but it could be. I think outside of computer science context, port and portal are probably related, etymology-wise. So this in this case it's 32 bits. So each of these numbers is from 0 to 255, so that's a byte, 8 bits worth of information. So this whole thing makes 32 bits worth of addresses, and that 32-bit number identifies a machine. And then our port is typically from 0 to 65,535, so that's 16 bits. And that identifies a particular connection point on the machine. So 65,000 ports, 4 billion machines. And the address space is interesting. So first of all, we ran out of address space a few years ago, right? There are more than 4 billion worth of addresses or reserved addresses on the internet, right? The one that we all connect to. So we do IPv6, which is, I think, 48 bits. I'm not sure. Yeah. I haven't made peace with this yet. But I met the person who claimed this was his fault, a guy named Vint Cerf. And he said that when they were, specking this out and doing this, there was a debate between, should we do 32 bits, 64, 48, and he managed to convince the other people on the team, let's just do 32 bits just to get this working. And if it looks like it works, then we can go back and make it larger, right? And that was like decades ago. And so he claimed it was his fault, but I've heard others. But yeah, Al Gore invented all of this. But how many of us have done this, right? We'll get this working and then we'll go back and do it right. And it doesn't happen. So that's one thing, right, is we run out of space pretty quickly with this. But the other thing is, most of us, we live on an intranet instead of an internet, so it's a local network, right? And we only have to discriminate among the devices on that local network. So I've got, a few laptops and some printers and some phones and some tablets and things like that. But all of the things that I have connected to my local network are 192.168.0. And I got 256 choices here. I haven't used them up yet. I got some Raspberry Pis and stuff like that, but 20, 30 devices max. Plenty of address space. But when you go to the outside world, right, this is not your network address, right? And so if I do a who, right, I'm logged onto the server as test. there's the IP address I'm coming from. Right, so that's probably my router. Don't hack me. And if you're on Clark's network, right, you have a different address, and that's not an address that's actually accessible from the outside world. That's on a big intranet, which is Clark's network. You know, there's routers that connect actually to the outside network, and so that's a whole nother story. And in a networking class, you'd get into all of that. But whichever case, whether this is an address on the internet or on a local intranet and so on, we have this IP address, and we put that together with a port number. And the port number basically tells us, you know, what are we trying to connect to? We're trying to connect to, you know, an SSH server. We're trying to connect to a print server, a time server, and so on and so forth. So let's eyeball some port numbers. So if you look at a Unix machine, look under /etc/services, you'll see a list of port numbers. And these are standardized. They're agreed upon. They're not, you know, intrinsic to anything. But the understanding is that port 7 is a echo server. So if you make a connection to port 7 on a machine, whatever you send should get bounced back. If you make a connection to port 21, that's an FTP server, file transfer protocol. So you can exchange messages with the server and use that to send or receive files. Now, most of these are shut down. There's nothing sitting around listening to these ports. It's generally considered bad security to have open ports, to have a port that can be connected to, because, you know, old software can have a buffer overrun exploit capability or code injection or things like that. So most of these are disabled. And some of these, like FTP, this is blatantly insecure, right? Because FTP didn't do encryption. So if you tried to log into a machine to do file transfer, you type in your password, those bytes were just going across the network. Now, when your network was, you know, physical wires, that was a certain measure of security. But now it's wireless. Everything is accessible, right? So you never send passwords in plain text and so on. Port 22, on the other hand, that's the SSH port. That's got encryption, right? So before you send your password, it gets encrypted locally and sent over and then decrypted on the other side. So that's more secure. Port 23 is a telnet. Daemon. Telnet is the unencrypted version of SSH, basically. It's just raw, send data, bring data back. We'll use Telnet in this class. Yeah, Telnet existed first. But the cool services seem to be odd-numbered. And so I think SSH slipped in an even-numbered spot. But I don't know. There's probably a better reason. But it was 21, 23, 25. So 21 was FTP, 23 was Telnet, 25 is Simple Mail Transfer Protocol. So SMTP. And we'll use Telnet when we start developing some code for working with this stuff in Java. Telnet's a really easy way to make connections to ports. You don't want to send secure information over it, but other than that, you know, it's a perfectly fine tool. So there was a time server on port 37. There was a whois server that would give you information about name resolution and so on. Most wireless routers have a telnet server, really. Never thought about that. So port 79 was a finger server. So, right, you could say finger and put in a username and get information about that user, like my phone number that I never answer because I probably have a million messages on there by now. And so you could talk to port 79 on a different machine and give it a username and get this information about somebody on a machine other than your own machine, including what their plan was, their project, when they logged in, and so on and so forth. Again, most of these things don't work anymore, but there were ports agreed to be set aside for different uses. I don't think Gopher still works. Gopher was awesome. Yeah, I think that went away. Yeah, that was back when we were starting to see like little glints of light that were like, wait a minute, what's happening here? Archie and all of that stuff. And you were starting to see that the world was changing, and there was like something really cool coming. Yeah, IRC, or Usenet, if you want to go back further. Now Gopher was pretty far back. All right, so Minecraft, right? There's a Minecraft server. It's port 20,000 something. Oh, UUCP, nice, yeah. Unix. There we go, 25.565. So that's the Minecraft server. So if you have a Minecraft server somewhere, there is a program running on a machine connected with that port number. And when you want to log into that server and play on it, right, you run a client program on your side, which basically goes to that machine and says, hey, you there on port 25.565, I have some information for you. $361 Gopher servers, cool. All right, so all these port numbers below 1024, those are privileged. You can't use those unless you're root, but the ones from 1024 on up are just kind of Wild West. And this is an interesting file to look at. We don't really need to use it a whole lot, but it's always there in a Unix system. So Kermit was an old file transmission system that wasn't network based. It was just phone line. It would just use characters. But it was a pretty good file transfer program. And I don't know what most of these things are. Yeah. All right. So, this takes us to the idea of sockets. So, I don't like repeating myself because I told this story in the morning class, but I didn't tell it in this class, so I have to repeat myself sometimes in lecture, and it always feels weird because I feel like one of those people who tells the same story again and again. So I'll tell you the story. So when I was in high school, we had a computer terminal in the library, and it was connected to a computer at a place called BOCES, Board of Cooperative Educational Services. And that was, an agency in New York that was involved in education. And they ran a PDP 1170 computer, kind of like a mainframe, but really a mini computer. And that computer was used by a number of schools, about 20 different schools in southern part of New York State. And so each school had, a few terminals that were connected to this one machine. You could log in, you could run programs, and so on and so forth. And we weren't allowed to use it, first of all, so we'd sneak in and hope nobody noticed us, which was hard because it was a line printer, so it would make noise. But as we'd play around with it and we'd look around, we realized that, there were other schools connected to this machine, and so there were other people logged in. And so, here was my school. And, here's some other school, and we're both connected to the same machine, right? So a single CPU with a single disk drive, and, there were file permissions. You mostly owned the files you created, but you could set permissions so other people could access them. And so we figured out we could talk to people on other machines if we cooperated. So here's the way that we wrote our first chat programs. Right, we would agree that, for example, I would create a file called, nick.txt, and I would put some message in here. And the person at this other school would periodically come in and look to see if there was a file named nick.txt, and if there was, they would open it up and they would read the message that I had left for them. And then they delete this file. And then if they wanted to send a message, they would create a file with their name, say sid.txt, with some information, and the next time I logged in, I'd look and I'd see sid.txt, I'd read their response, and then delete it, and they'd know that I read it. So we could send information from one person to another by using files. And once you can do that, you pretty quickly get to the point where you write a program to do this. And so you write a program so that when you type in a message and you hit enter, it drops it into a file named nick.txt. And this person over here is running a program which every second looks for this file, and when it finds it, reads the contents, prints it out on their display, and then deletes this file. And when they type something, it goes into a sid.txt, and my program is constantly looking for this file, opens it up, prints out the contents, and deletes it. And so you could make an interactive chat program to allow two people to send messages back and forth just by using files. And you need to get a little more, a little fancier with this to make sure that, you know, this person doesn't read and delete a file while I'm in the process of writing it, and so on and so forth. But you create tag files, and first you make the file, and then you create a tag file to say, hey, there's a file there, and so on. Sorry, looking for an ink cartridge. And so you could do rudimentary networking like this. And what we do today is functionally kind of the same thing. But using files is crude, right? But the idea is this was something into which I could send characters and from which somebody else could read characters. All right? Now we can do that, you know, in a Unix to Unix kind of way by using a pipe. And a pipe, you know, we think of as a conduit. You write something in here, you read it out from the other side. So in networking, what we use is something called a socket. And if you look up the definition of a socket in the original RFPs, it's called an endpoint for communication, which I don't know what that means, but it sounds cool. But here's the idea, right? Here's your server, and this is sitting on some machine, so, you know, 192.168.0.17. And there's some point of communication. This is a socket, and it has a port number. So maybe this is port 87. And so I can have a client program, and I can identify this machine if I know its address, and I can identify this port if I know its port number. And I can say, hey, I want to talk to port 87 on machine 192.168.0.17. And I can get to the server like that. And then I can start a two-way exchange. And so, for example, so Telnet is a program that lets me connect to a machine and a socket. And I can say Telnet 127.0.0.1, and I want to talk to port 25. Now, 127.0.0.1, that's always yourself. It's a special address that's set up to point to yourself. So I'm talking to port 25 on the Linux server. And this is a daemon running that's running SMTP, Simple Mail Transfer Protocol. So I can say hello from me, and it says hello localhost.local domain. And I can say mail from you know, the universe, spelled wrong, and I can say recipient to, and let's send it to test. That's my user ID, and I can say data, and I can say hello there, this is weird, goodbye, and then I can end by just putting in a period. And it says that's been queued as some hex number. So I can quit out of here, and guess what? I've got mail now. And if I go into my mail program, it tells me I have mail from the universe. And it says, you know, it's from the universe at localhost.local domain. So this is how mail used to get sent. Now it's done differently now, but basically when you wanted to send mail to somebody on a machine, you would make a connection to port 25 on that machine. And there was a mail daemon hanging out there, a server, that would see that connection, have this exchange with your mail client, where you would say who the mail's from, who it's going to, and what the body of the message is. And then it would basically drop it into a special file with the user's name. And when you run your mail program, when you've logged in, it reads this file and looks for mail messages. So none of this is magic, right? It's really just data transfer. And networked communication is really just kind of doing the same thing you could do by just reading and writing files, except instead of files we have this fairly magical conduit called a network. And so we can send information into other machines and get it back. All right, so that's our setup. We're out of time. So what we'll do tomorrow is we'll start writing some Java code. We'll cobble together a server in Java. Very little code, right? It's going to be really painless to do this. We'll make a server and we'll talk to it through Telnet. And then we'll start talking about how we make a client. And then once we have a basic client-server pair, we're all set for PA5, which will be the networked version of DOTS. All right, so that's our plan. Enjoy the afternoon. I will see you next time. I have not heard of WebSockets, I don't think. Unless I know it by a different name.